Hi guys. In this video of geometric proofs, we're going to cover proofs using definitions. This video is going to have 5 examples, so let's get started. So in this first example, we have that ABCD is a parallelogram. The first thing you should notice is that the given in these proofs compared to the givens in the previous proofs in other videos is very different. So let's get started by writing down the given. In these proofs involving definitions, it is critical that you write down the given word for word. That is the most helpful thing you could do because that establishes all the information the rest of the proof is going to be based off of. In my opinion, when we have a shape and you could define that shape, these proofs could be way more straightforward than previous proofs where you have to hunt out the parts. So, in a parallelogram, opposite sides are parallel. That is the definition of a parallelogram. I'm going to use that definition to my advantage by stating that AD and BC are parallel and DC and AB are parallel. So let's write that up. What I did here is that I separated the two statements on the table by color so that, just to clarify, what supports what I wrote. And if you notice, I used the same reason twice. That means if I wanted to, I could have just written this on one line. It would just use a comma. I will do that for the next part, which is using the alternate interior angles that are a result of the parallel lines. So let's take a look at that. One of the things that students often struggle with is which angles associate with which set of parallel lines. So hopefully this is an opportunity to help you with that. And this angle, angle 3, which is associated with the green angle, and angle 4 are alternate interior due to AD and BC being parallel. If you don't want to use the numbers, you could say here this is angle DAC and this is angle BCA. Now let's take a look at the other side. So this side gets the red alternate interior angles because it's associated with the red arrows. Hopefully that pattern's kind of clear. And again, this angle is DA and this angle is BC. Okay, let's write that up. Hopefully the color coding helps clarify where the sets of angles are coming from. Alright, so now that I have two sets of angles, I have that reflexive side in the middle. So I'm going to use that. I mentioned in the previous video that the reflexive property is probably one of my most commonly used tools when proving. It often helps us find that side that we just need. And it's ever present because proofs often split up a quadrilateral into triangles. Alright, let me take an inventory of what I have. So here I have an angle, this is a side, and that's an angle. Here I have an angle, this is a side, and that's an angle. I check my inventory on my table, and an angle here, an angle written here, and that's a side. Remember, on the table, you do not need to have your elements or your evidence in order. I marked off the diagram to make sure I know which postulate I have, and in this case, I have angle, side, angle, so I can now state that my triangles are congruent. Okay, so one thing I should point out is I was very careful here to make sure I stated my triangles in corresponding order. I did not use the same order as I did in the angles, like I did in my previous video. But when we're going to start proving different parts of triangles, like we are in this case, we are going to really want to rely on the corresponding parts that we have. So let's take a look at the proof. Okay, so here we want to prove that AB is congruent to CD and BC is congruent to AD. In this case, I can write this all at once on the same line because I know that I'm going to use the same reason. But if you are not sure, you could separate that proof into two lines, or you can do your investigation first. Now, as I mentioned in my previous video, proving parts of triangles are congruent, I cannot make the marks I'm about to make until after I have proven the triangles are congruent. And here's what's going on. The proof wants me to show that AB and CD are congruent and BC and AD are congruent. In the previous video, I mentioned or asserted that you cannot make an assumption that sides that are parallel are also congruent. This is further evidence of that. I have to find evidence of these properties separately. In this case, I can state that AB is congruent to CD and BC is congruent to AD because the triangles are congruent. That is typically written as congruent parts of congruent triangles are congruent. That is one way to write that. If you watched my previous video, you would know that I have a serious issue with the acronym CPCTC, so I avoid that at all costs. Typically, if I am doing this proof or showing my students this proof, I just say you can back up this statement by stating that the triangles are congruent, because that supports the fact that the parts of the triangles are congruent in itself. But sometimes, or oftentimes when proving, we want to be specific in the use of our theorems. Okay, last thing on this example. This example is proving a property. So this is a property of a parallelogram, not a definition. It's splitting hairs for sure, but that's how we know of the properties of things like parallelograms, squares, and rectangles, and kites, and whatever else we have out there. And knowing these properties helps us know how to build things, which, in my opinion, all proving is just a discussion on building theory and how different shapes go together so we know that things are structurally sound. Alright, let's take a look at the next example. Okay, so I once again saved you the trouble of watching me write down the given. I know that upsets you guys. But what we want to do here is we want to prove that we have a parallelogram. Well, we have to remember what the definition of a parallelogram is, which is that opposite sides are parallel. So I cannot use opposite sides are congruent because that is a property of a parallelogram, not a definition. Here we go now. So I'm going to do this just like before and prove that my triangles are congruent. I'm going to start with the parallel lines. My students know me to be very repetitive. When parallel lines appeared in all of the other videos, I stressed how to find the alternate interior angles, and the reason why I push that so much is because it is one of the major errors I see in proving. So remember, only angle 1 and angle 2 are congruent here. I do not have other angles that are congruent. And that is because those are the angles associated with the lines with the arrows. So those are my alternate interior angles that I can use. And remember, I could use the letters or I could use the numbers. That is entirely up to you. So I could say angle 1 and angle 2, or I could say angle DCA is congruent to angle BAC. I am sticking with the letters for this proof because I find that my students often get more confused when we just use the numbers in these proofs. Next, I'm going to use that reflexive side. Part of the reason why it's important to state the given verbatim or word for word and pay close attention is because once again we are in a situation where the parallel sides provided are also congruent. We cannot make that assumption. Now let me take an inventory of what I have. And this is an angle, this is a side, I have a side here, this is an angle, and this is a side. And here we go again with side angle side. It seems to be a very common postulate I'm using in all of these examples. I have my triangles congruent, so I can make that statement using the postulate side angle side, which backs up all of my evidence. Keep in mind here, and I did not mark off the table, I have a side, I have an angle, and a side, everything is listed. In this case, it's nice and clean and organized in the order of the postulate. So, now comes the next step. I have to prove that I have another set of parallel lines. AD and BC need to be parallel. The way I'm going to do that is I have to find another set of alternate interior angles. Once again, after I have proven that my triangles are congruent, I'm going to use my tools to prove that these lines are parallel. And I want to prove that AD and BC are parallel. I am putting those arrows in there after I have proven my triangles congruent to see where my alternate interior angles are. I am creating, with the facts that I have, the exact scenario in the previous example. This is a great example to show you how powerful math really is. And it's an exceptional power to have. So, I know that I have alternate interior angles here and here. Well, I should say congruent angles there and there. I am going to make the statement that angle DAC is congruent to angle BCA because the triangles are congruent. So I guess I'm going to say this a little bit more plain English. I'll say angle DAC is congruent to BCA because triangle ADC is congruent to triangle CBA. From there, I could use that fact to state that AD is parallel to CB. Keep in mind, we have that AB and DC are parallel. So let me erase some of this so you can see how I'm creating this scenario of opposite lines being parallel. Now, the statement I can make is that they are converse alternate interior angle theorem. You can use that language, or you could just say that angle DAC congruent BCA are alternate interior angles. From there, I can now make my final statement. I could state that ABCD is a parallelogram because AD is parallel to CB and AB is parallel to CD, which is opposite sides of A, B, C, D. Can't argue with that. The other thing I think you could say is that is the converse definition of parallelogram. ABCD, something like that. Either way is fine, but I've made very clear that I know that ABCD is a parallelogram by definition. So I could even write by definition if we really want to be a stickler. Alright, personally, I find these proofs to be a lot of fun. They are challenging. You really have to apply what you know, but they take all of that time that you spent learning about different shapes and putting it to good use. And they are very investigative proofs, very diagnostic. Alright, let's take a look at the next example. Okay, in this example, we have a kite. And the definition of a kite is that it is a quadrilateral with adjacent sides that are congruent. And if you're thinking to yourself, wow, this guy really knows his shapes? Well, I used the interweb and looked up the definition. Now, let's get started. We're going to prove a property of a kite. And this might get a little tricky. Let's take a look at how it goes. So the first thing I'm going to do is I'm going to use the adjacent sides to prove my triangles are congruent. Once again, I split this up into two lines, but you absolutely could have used one line here. I should also point out that I failed to point out at the beginning of the example is that this is the first time I'm doing these two proofs, this example and the next one, in a very, very long time. I think it's been probably about 10 years since I've done this proof. Now what I'm going to do is I'm going to use that reflexive side. So I have the reflexive side, and what it looks like as I take an inventory of the evidence I have found is that my two triangles are going to be congruent by side, 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 which is a nice change of pace because just about the last 4 proofs I've done have involved side angle side. Now, let's make the statement that my triangles are congruent. And in this proof, I can simply state that angle DAC is congruent to angle BAC because the congruent parts of congruent triangles are congruent. Or the triangles are congruent, so are their parts. However you want to communicate that. That is one of those things I know I keep repeating. And I am pretty sure that the diagonal of a diagonal of a kite bisecting top angle is a property of a kite. But for some reason, we didn't make that statement in this example. All right, let's take a look at the next one. Okay, in this example, we're going to prove a property of a kite. The property we're going to prove, coincidentally, is the property of a kite that gives the geometric shape stability when you fly it. It's part of the reason why this shape is so common in the kites that we fly. I really have to strategize here. I have not done this proof in a long time either. And what I want to prove is a set of diagonals bisect each other. I don't need to prove the big triangles here. I can prove these small triangles here. Then, from there, show that these DE and BE are congruent. In that case, I have to use the property that I showed in the previous example, which is that angle DAC is congruent to angle BAC. Thankfully, it was provided in the given, so I don't need to go hunting for evidence for that. That's my strategy. Let's get started. I marked off the angles in the given, then I know that DA and AB are congruent because that is the definition of a kite. You can also have supported this statement by saying definition of kite ABCD. Either way would have been fine. AE is a reflexive side, so I'm going to use that. And now I'm going to take an inventory of the parts that I have so I can see if I can prove my triangles are congruent. I have a side here, an angle, and a side here, angle, and a side. Angle here, a side, and a side. Kind of a bad word, but that's why it's important to label your diagram and not worry about the order of which you write your elements or your evidence on your table. So I can prove these triangles the same by the postulate side angle side. Once again, this video is packed with a lot of tiny details that we have to be aware of. Notice in the angle that I have written on the given says angle DAC, but the triangles, as I started this example with, are triangles DAE. Angle DAE and angle DAC are the same. It does not matter to notate this angle if I stop here or if I keep going. Those angles are the same. Okay, let's finish this up. Because the diagram is small, I cleaned this up for you a little bit. The triangles I proved were these two triangles here. Now, the sides I can use to show that one set of diagonals is bisected is DE and EB. So I can state that segment DE is congruent to segment EB because triangle DAE is congruent to triangle BAE, so are their parts. Yet another way to write CPCTC in normal language. That point there, that DE is congruent to ED, backs up that DB is being bisected. So DB is bisected by AC, DE, and is congruent to ED being the reason, with AC between them. We can say that. We can say the word AC included. Or we can say the converse segment bisector theorem. Now that backs up my point that I want to prove. So I could state that one set of diagonals is bisected in a kite because we know DB is bisected by AC. Very challenging proof right here. Alright, let's take a look at the last example. Okay, in this example, triangle ABC is isosceles. What does that mean? Well, the definition of isosceles is a triangle with congruent sides. A property of an isosceles triangle is congruent base angles. So we are once again proving a property of a definition. Let's get started on this by once again proving that the triangles are congruent. And I could start by saying that AB, side AB, and side AC are congruent because triangle ABC is isosceles. Once again, I like to use, definitely for beginner provers, the language from the given. You can definitely have written here the definition of isosceles triangles. That would have been okay. I also have that bisected angle, so let's address that. I've spent a lot of time talking about bisected angles and midpoints. You can go back and check out that video. But essentially here what I have is angle BAD and angle CAD are bisected. So let's write that up. You'll notice as we reach the end of this video series, I am talking and speaking to the more formal methods of proving. I am speaking to the formal language that you will see as you advance in proving. Once again, I just am using the language from the given, but you could have stated that this is a definition or a property of a segment bisector. That's probably the way it would come up if you were to Google this proof outside of this video. I am now going to use the reflexive side, and oftentimes that is written as reflexive property or reflexive sides are congruent to themselves. I'm now going to take an inventory of what I have to make sure I can prove these triangles are congruent. I labeled my diagram side, angle side. Let me make sure that I have listed all of my elements, which I have, so I can now state, using the postulate, once again, side angle side, to prove that triangle ABD is congruent to triangle ACD. Triangle AD by side angle side. That's about 7 side angle side proofs in the last 2 videos. Okay, now to prove the property of an isosceles triangle, which is that angle B is congruent to angle C. I don't really need to mark up my diagram here for this one. Again, if you're going to do that, make sure that you're doing this after you prove your triangles are congruent. I know I've harped on that for the last 2 videos as well, It is the most common error I see, next to CPCTC being written all over these proofs. You have to know and be paying attention to the work you're doing and make sure that you try to keep in mind what it is you're looking for. So angle B is congruent to angle C, and I'm still going to avoid CPCTC at all costs. So congruent parts of congruent triangles are congruent, or CPCTC. Okay, guys, this is a monster video here. If you started this video at the beginning and watched it straight through to the end, you should congratulate yourself and your work ethic. It's pretty incredible. I hope that you guys found this series on geometric proofs helpful. If you watched all of the videos, at this point, you probably have just about everything you need to work through a geometric proof, beginner to intermediate. There are a few theorems and postulates you can use, or theorems and axioms, however you want to look at those, as we get to more advanced proofs, but all the proving I have done usually are combinations of the proofs you have seen here, which are proofs or which are elements from the other videos as well. So I hope that this video series was helpful.